So now we're going to learn about position time graphs. And we've talked about velocity, and we've talked about position and displacement. Another way to represent them is on a graph, because position might change over time. If you're in motion, if you're traveling, your position from a relative point might be changing, and we can use a position time graph to show how your distance changes, your displacement or your position changes over a certain time period. So that is essentially what a position time graph is. And what you see here is a position time graph for a rolling ball. You might remember from your grade 9 rise over run for the slope of a line. Here we see the rise of this linear equation is 40 meters. Its run is 10 seconds. If we divide those, we end up with a rise over run value of 4 meters per second east. And what you'll find is that is actually the velocity of this object that is changing its position. And that's how we use position time graphs. We can use a position time graph not only to find the position of an object relative to a starting point, we can also find its velocity by analyzing the slope of a line segment that occurs on the position time graph. So that's what they're going on with here. I've already kind of talked about it a bit, but finding the slope is the change in position over the change in time. You might have noticed that change in position over change in time was the same as the velocity or average speed or average velocity equation, and that's why it is equivalent to finding the velocity or the speed. So here, what's the slope of the line? It's 4 meters per second east. It's 40 divided by 10, and that represents the velocity. So in green, this is also another way to represent important ideas. So whenever you see something in green, it might be worth writing that down. The slope of a position time graph gives the velocity of an object. The steeper the slope, the greater the object's velocity. So here, this question says, prove that the slope of a position time graph gives the average velocity. Well, I've already sort of said this. M equals delta D over delta T. That's the same as the average velocity equation, delta D over delta T, the change in position over the change in time. The next part here, we're going to look at some graphs. This was done a bit differently before, but we're just going to talk about the graphs, and we'll just talk about them and see whether we see an object moving and how fast it's moving. So here's one position time graph. Let's say this is the position from a person to a basketball, and it is a non-zero position because the person is not holding the basketball. But neither the person nor the basketball is changing their position, so no velocity, the velocity would be 0, because if we found the rise over run of a horizontal line, it would be 0, and essentially we have no motion happening. That is one type of graph you might see, a position time graph. Whenever we see a flat line like that, a horizontal line I should say, no motion is occurring, velocity is 0. Here's another graph. Now the basketball is on the other side of a person, which might be considered a negative position. But again, the basketball and the person are not moving relative to each other. So we have a velocity of 0. The rise over run of that horizontal line is still 0. Now if I had a graph that looks like this, this might be a person who is traveling on their bike, coasting at constant velocity. Their position is changing at a constant value with respect to time. If you find the slope of that graph, that position time graph, you will find the velocity the person travels. So a line segment that is a linear equation would be a constant velocity. So this person's traveling at a constant velocity, and when you're traveling at a constant velocity, your velocity is not changing, so you're not accelerating, you're not decelerating. That means you're not going faster or slower, you're going at the same speed the entire time during that line segment. Now, if you have a negative slope, this would be somebody moving toward a home position. So if I have a positive slope, I'm moving away from my reference position. A negative slope means that I'm moving towards that position. Or I'm moving away from that position in an opposite direction. So these are all linear equation graphs, and the type of motion is uniform motion. Uniform motion is no acceleration. So we'll also look at this with acceleration a bit later, so we'll get into that. But first, let's look at some more complex position time graphs. This is where we have multiple line segments. So here we have a position time graph with a segment A, segment B, and segment C. And we'll talk about what's happening in each segment. So for segment A, we're starting at position 10 meters west, and segment A we end at position 30 meters west. It took 5 seconds to make that change in position from 10 meters west to 30 meters west. For B, we're at 30 meters west at the start of the time segment, and we're at 30 meters west at the end of the time segment. So no motion occurs during the 10 seconds that we are in line segment B. For C, we are starting at 30 meters west, and we end up going home at which is 0 meters after 5 seconds. Here, because we're going back home, we have a negative slope for C, whereas A, when we're moving away from the home position, we have a positive slope. Next question here says to determine the displacement and the velocity. Well, the velocity is the slope. So let's open up our camera here, and we'll look at calculating the slope for that line segment. So for line segment A, the slope is found by finding the change in the position, which is 30 meters west minus 10 meters west over the time, which is 5.0 seconds. 30 minus 10 is 20. 20 divided by 5 would be 4.0 meters per second west. For A, the change in position, the delta D, we have gone from 30 meters west minus 10 meters west, and actually I shouldn't be concluding this direction here because we're looking at just a distance. That would be 20 meters. Actually, they do ask for the displacement, so that would be 20 meters west. I just read it again. Let's look at line segment B. This one's probably going to be the easiest one to calculate. For line segment B, we are not changing our direction at all. Or I guess we could say we're at 30 minus 30, which is 0. And we're doing that for 10 seconds. So we have 0 meters per second is our velocity. Our displacement is 30 minus 30, so our displacement is also 0. And then for C, we start with for our velocity, we start at 30 west, or actually we have to subtract by that because we have to do this the other way around. Our final position is 0, and we have to subtract 30 west. That works out to, if I rewrite that, sorry, this is over 5 seconds. If I write that as east being negative, I have 0 minus negative 30, which becomes 30 over 5, which is 6.0 meters per second east. That's my velocity. And when I look at my displacement, do it on the side here, that would be equal to my final direction, which is 0, minus 30w, and that, gotta move it over because you can't see it. That would be negative 30w, which is the same as, so negative, I'm going to change this to east, negative minus 30, which becomes 30 meters to the east. So that is my calculation for this more complex position time graph. Here it says, what would the distances and how would the distances and speeds compare? The distances and speeds would be the same as the displacements and the velocities, but we wouldn't include the direction. Here's another position time graph, or actually it's the same position time graph, but different questions. What's the total distance and the total displacement? So here, to find the total, what we could do is, let's look at how this changes over time. Our total displacement, our total distance, for line segment A, we go from, we travel 30 minus 10. During line segment B, we don't have any travel. During line segment C, we go we end up at 0, but we travel from 30 to 0. So altogether, this is 20 plus 0 plus 30. We have 50 meters of travel. And our displacement, though, all we have to do in this case is look at our final position minus our initial position. And our final position is 0. And our initial position is 10 west. And minus 10 west would be the same as 10 east. For the part B to this question, sorry, I should include that there. The part B to this question, we're asked what's the average speed. So I've already calculated here the average distance traveled. So average speed is that distance 50 over the time, which is 20 seconds. So our average speed is 50 over 20. That works out to 2.5 meters per second. And my average velocity, is this showing up on camera? Yep. My average velocity is 10 east divided by 20, which works out to 0.5 meters per second east. Okay, now let's look at some more advanced position time graphs. These ones are not going to be linear, and we'll explain what's happening here. So in this case, somebody going down a downhill ski slope, they might start with at a home position, and then as they move down the slope, they're going to be accelerating due to the fact that gravity is now pushing on them. So their position will change at a showing, as this graph kind of shows, which would be sort of a quadratic change in the position. So we're moving away, we're speeding up, so we have a quadratic curve that is increasing. So if we were going in an opposite direction or moving away from the home position, it would be shown this way, where we have our position going down, but it is still moving, it's still accelerating away from a home position. So the first one is accelerating away from a home position in one direction, say east. The other might be accelerating away from a home position, let's say west. Now let's say somebody is trying to power their way up a mountain. They're actually going to be slowing down. Here is them slowing down as they go east or in a positive direction away from a home position. And then this is what it would look like if they were going in a negative direction from the home position and they're slowing down. So these are all nonlinear graphs, and they represent non-uniform motion. Anytime we have a position time graph that has nonlinear segments, it is either accelerating or it's decelerating, which means that we have non-uniform motion. This is what you should copy down for position time graphs. These are all very important points. The first is the y-axis is the position, the x-axis is the time. The slope of the graph is the velocity of the object. The more steeper the slope, the greater the velocity. If we have a linear shape, we have uniform motion with zero acceleration. If we have a nonlinear shape, a curve of any kind, we have non-uniform motion. Meaning the velocity is not constant, it is changing, and acceleration is not equal to zero. So now just because we have a changing curve motion doesn't mean we can't find the velocity. We can find what's called the instantaneous velocity, or the velocity at a specific point. And we can do that using 2 points that are very close together on the graph. And then finding the slope of those points. That would give us an instantaneous velocity at that specific point. And this, if you're interested, this is actually the introduction to the first problem that calculus solved, which is how do we find the slope of a tangent line of a curve. A tangent line being a line that touches a curve at just one point. And that is what calculus was used to solve. And this is something that we kind of touch on here, but you'll learn that a bit more when in your further studies. And this here again explains that what we're looking at is a tangent line to the curve, and then we find the slope of that tangent line. That gives us the instantaneous velocity. So let's say this graph here, what is the instantaneous velocity of an object at 2 seconds? Reading from this graph, you'd have to use the rise over run of that line. It has, we have a point at 4:12. We have another point at 2:4. So the change in the y is 12 minus 4, that's 8. The change in the run is 4 minus 2, that is 2. 8 meters divided by 2 seconds is 4 meters per second east. So instantaneous velocity, I want you to copy this down. It's the velocity at a specific instant in time. It's equal to the slope of the tangent to the position time graph at that instant of time. And the note again says, for motion with non-uniform velocity, average and instantaneous velocities are not necessarily equal.